Good morning, everyone. Today, we are going to discuss an exciting and essential aspect of our built environment, HVAC strategies and innovations. HVAC, or heating, ventilation, and air conditioning, plays a crucial role in our daily lives. It provides comfortable, safe, and healthy indoor environments. Given the considerable energy consumption of HVAC system, energy efficiency and sustainability have become central themes in this field. Today, we will explore innovative strategies and technologies driving the future of HVAC. Combined heat and power, or simply CHP, exemplifies efficiency by its core principle of producing both electricity and useful heat concurrently, utilizing the same energy source. Examining the benefits of CHP, we witness a process that contributes substantially towards energy conservation by curtailing waste. In doing so, it addressed a pivotal concern of our times, reducing greenhouse gas emissions, thus playing a vital role in our battle against climate change. Beyond environmental benefits, CHP also translates to financial savings, adding to its appeal. The field of CHP is characterized by consistent innovation, particularly in areas of control system and integration with renewable energy sources. This advance not only enhanced the process efficiency, but also strengthened the synergy between CHP and sustainable energy solutions, reinforcing its place in the future of HVAC systems. Among the novel concepts of cogeneration or combined heat and power CHP, we encounter the concept of cogeneration district cooling plants. Here, we see an efficient use of resources where the waste heat from gas turbine is ingeniously repurposed to drive absorption chillers. The heat source suitable to operate absorption chillers aren't limited to waste heat from turbines. In fact, they can include hot water or even direct fired sources such as diesel, natural gas, or steam. We also find the integration of CHP in the practice of district cooling, a process characterized by the distribution of chilled water from a central source through a network catering to multiple buildings. This setup essentially centralizes the cooling process, providing an efficient and economical solution for a large complex or cluster of buildings. For effective cooling within the building, specific equipment is necessary, including heat exchangers and water flow meters. It's essential to note that in many systems, certain requirements of temperature difference between the power supply, between the water supply, and return may influence the overall system design. Such factors need to be considered carefully to ensure optimal performance and efficiency of the cooling system. Heat recovery chillers is a product that captures and repurposing the waste heat, a byproduct of the cooling process. This technology bucks the trend of expelling excess heat, opting instead for its redirection to a secondary circuit, where it finds utility in a variety of applications, including but not limited to space heating and water heating. When examining the advantage conferred by heat recovery systems, one observes a compelling array of benefits. Primarily, they facilitate a notable reduction in energy expenditure. As waste heat is harnessed and put to productive use, concurrently they play a vital role in attenuating carbon emissions, aligning with global efforts to mitigate the impact of climate change. Additionally, the consistent heating solutions provided by this system serve to augment occupant comfort. Regarding their applicability, heat recovery systems showcase remarkable versatility, finding utility in various scenarios. These range from heating swimming pools to catering to hot water demands in laundry operations, extending even to realm of data centers, where they can efficiently maintain thermal comfort in office spaces. This diverse spectrum of application underscores the intrinsic value of heat recovery system within the HVAC domain. Chilled beams function on the principles of convection and have proven themselves instrumental in providing not just cooling but also heating in certain circumstances. What makes these devices particularly noteworthy is their ability to optimize energy efficiency. One can contrast the performance of chilled beams to traditional air conditioning systems to truly appreciate their potential. Quite often, chilled beams outshine their counterparts by delivering superior energy efficiency. However, their merit does not stop there. A crucial benefit and a determining factor in the overall health and comfort of the building occupants lies in the ability of chilled beams to contribute significantly to the enhancement of indoor air quality. Hence, when discussing innovative HVAC strategies, chilled beams stand out for their combined advantage of energy efficiency and the promotion of healthier indoor environments. A chill beam is a specialized device designed for handling sensible loads. Its function initiates by drawing primary air from an air handler, further directing it to the integrated air plenum of the chilled beam. Here, the air undergoes pressurization and is subsequently discharged through a series of meticulously engineered nozzles. The nozzles, characterized by their unique hole pattern, allow the air to be released at an elevated velocity. This swift stream of air results in the formation of low pressure zone, which in turn facilitates the process known as entrainment. Simply put, the entrainment describes the induction occurring via the water coil due to the pressure differential created by the high velocity airstream. The process is similar to the observing the wind effects outdoors. Air tends to follow the path of least resistance when faced with differential pressure. The mixing chamber located behind the chilled beam's water coil and near the nozzles act as a low pressure zone. Naturally, due to the pressure differential, air is inclined to move into this chamber. Examining the case of chilled beams, specifically a heat exchanger coil charged with either chilled or hot water, treats the air as it's drawn in from the room. Through this entrainment process, the chilled beam facilitates the transfer of energy from the air to the water coil. Natural convection is a fluid flow produced by two separate fluid densities, where one is heavier than the other. The passive chilled beam achieves this by bringing in water, which is the temperature is around 24 or 28 degrees C, which is colder than that of the surrounding air, which is around 30 plus degrees C. So, therefore, it makes the air around the coil denser. This makes this cold air sink, draws the warmer and lighter air above it down through the water coil and cools it off. Thermal energy storage. This technology represents a strategy that stores the thermal energy for subsequent use. The benefits offered by this technique are multifaceted. Primarily, it allows the shifting of cooling loads to off-peak hours, thus optimizing energy use. In doing so, it results in a considerable reduction in energy costs. Furthermore, it aids in enhancing the comfort levels within the environment it serves. Various instances of this technology abound. For example, ice storage is an efficient method of storing cooling energy. it is to be used later when required. Water thermal energy storage and phase change thermal energy storage are other viable methods, each with their unique attributes. The promise of thermal energy storage technology lies in its potential to augment the efficiency and reliability of HVAC systems. With ongoing advance in this area, the future of thermal energy storage appears promising, and it is poised to play a crucial role in shaping the next generation of HVAC systems. Water thermal energy storage, or WTES, utilize water as the storage medium, leveraging the thermal properties of water to efficiently store energy. The working principle of this system is an efficient one. During off-peak hours, when energy costs are typically lower, water is heated and stored. This stored thermal energy is then harnessed during peak hours to cool the building, thereby achieving an effective and cost-efficient management of cooling loads. WTES system present a particularly viable option for buildings with substantial cooling loads and for those situated in regions with high electricity price. This methodology not only ensures efficient use of energy, but also contributes significantly towards economic savings, making it a valuable inclusion in our arsenal of innovative HVAC strategies. In today's discourse, we have traversed the landscape of HVAC strategies, focusing on several noteworthy innovations and technologies that hold the potential to transform this domain. We began with an exploration of cogeneration, or combined heat and power, CHP, a process that concurrently generates electricity and useful heat from a single energy source. The standout benefits of CHP include a reduction in energy waste and greenhouse gas emissions, as well as significant cost savings. We delve into the realm of chill beams, which are sensible load-treating devices that improve energy efficiency and enhance indoor air quality. Further, we examine cogeneration district cooling plants, which harness waste heat from gas turbines to drive absorption chillers, and district cooling, which provides efficient and centralized cooling solutions. A significant portion of our discussion focused on heat recovery systems, which capture and reuse waste heat from cooling process. This system contribute to energy conservation, carbon emissions reduction, and enhance occupant comfort. We also examine the role and potential of thermal energy storage in HVAC system. This technology allows for shifting cooling loads to off-peak hours, reduce energy costs, and improve comfort levels. In conclusion, these innovative strategies and technologies represent substantial advancement in HVAC systems. They offer promise for more efficient, cost-effective, and environmentally friendly solutions, demonstrating that the future of HVAC is ripe with potential for continued innovation and improved performance. With that, thank you for your time and see you in the future lecture video series. Thank you.